hear the introduction, but I'm sure they can look you up. So our speaker today is Jaskot, in case you're joining us on YouTube. Just to
All
quickly
right.
recap, looking for volunteers for next year. So if you're interested in giving a talk and just listening to this, please reach out to myself and Benny. All right, Anne, take it away. Thank you.
All right. So hopefully you can see my screen and just the one slide. Is that right? Okay.
Yes,
Great.
correct.
So I'm Anne Jaskot. I'm at Williams College, and my research focuses on the far ultraviolet, specifically the production of ionizing photons in star-forming galaxies and how they make it outside of galaxies. And today I'm going to start by talking about why I think that topic is important and interesting, and then I'll summarize some of the recent work that I and others have been doing at low redshift. And I'll end with some of the open questions that I think HWO will be particularly well suited to answering. So one of the reasons this topic is important is that ionizing radiation sets the story of hydrogen, the most abundant element in our universe, which only has 3 chapters in that story. It was formed at the Big Bang. It recombined and became neutral at redshift of 1100 or so. And then with the formation of the first galaxies, it became ionized again as ionizing photons or Lyman Continuum photons escaped those early galaxies into intergalactic space, gradually ionizing the hydrogen in intergalactic space over a period of some time, a process called reionization. And this process was completed about a redshift of 6 or so. And this is a signature of the formation and influence of the first galaxies. It's a time when they dramatically changed the state of the universe as a whole. And also by studying and understanding this epoch, we get insight into the properties of early galaxies themselves, what sources they contain, how feedback operates in these systems, and how galaxies as a whole influence the surrounding intergalactic gas in the universe. So with JWST, we are actually now directly detecting large samples of galaxies in this epoch, photometry now for hundreds of galaxies. This is from back in 2022, some of the first results from JWST. These are showing spectra of lensed galaxies, and these 3 here are at redshifts of 6 to 8 in the epoch of reionization. So thanks to JWST, we can now study and learn a lot about the actual properties of galaxies at this time, getting masses, radii, nebular conditions from line ratios, Lyman alpha in some galaxies even. So it's really an exciting time for that. And this is one of the key science themes of JWST is understanding this process of reionization with some of these identified key questions. When and how did reionization occur? What sources caused reionization? And what are the first galaxies? So answering the first 2 of these questions about reionization itself requires understanding how ionizing Lyman continuum radiation actually makes it outside of galaxies. How much of that actually escapes a galaxy into intergalactic space without being absorbed by a galaxy's neutral ISM before it can ever go outside the bounds of the galaxy. And so we need to understand the Lyman continuum escape fraction. That is, what fraction of a galaxy's ionizing radiation escapes into the intergalactic medium. And there are numerous competing theories for what processes regulate escape fractions, what the properties of the dominant reionizing galaxies are. One of the most basic ways we can think about these different contributors is by classifying them on the basis of luminosity. And even here, there are competing theories, whether perhaps the brightest galaxies in the epoch of reionization dominate the process with the highest escape fractions, or perhaps the much more numerous fainter galaxies dominate this process. Moving beyond just luminosity, we can think about the physical processes at work that drive escape fractions and that might enable a galaxy to contribute more or less ionizing radiation. And feedback is really central to this. One main proposal that also shows up a lot in simulations is that supernova-driven outflows are essential for creating high escape fractions, where supernovae from some concentrated burst go off and drive outflows that clear out and disperse the ISM, allowing these pathways for ionizing photons to escape. But this isn't the only possible way to get ionizing photons out. It could be that some sort of just clumpy geometry in the interstellar medium combined with strong ionizing radiation itself can fully ionize particular sightlines, and you may not need supernovae at all. these are just this is just a taste of the different things that have been proposed. Many more ideas have been put forward as to what sources might contribute: AGN, high-mass X-ray binaries, other processes, galaxy mergers that might disrupt the ISM of a galaxy. So there's many different ways that the properties of galaxies might influence this parameter. Actually, constraining Lyman continuum radiation coming from a galaxy observationally is very tricky. And in particular, it's improbable or impossible at the epoch of reionization itself because of the attenuation in the intergalactic medium. So this plot is showing the IGM attenuation at the Lyman continuum in magnitudes as a function of redshift. And this just gets uncomfortably high by the time you actually are looking at galaxies at reionization, where almost all of that radiation would be absorbed long before it ever reaches a telescope on Earth that could detect it. So we can't directly measure Lyman continuum from these reionization era galaxies themselves. And so we need to understand what regulates this process, we need to look at lower redshifts to try and identify Lyman continuum emitters there. There have been many efforts at intermediate redshifts, sort of the 2 to 4 range that I don't have time to summarize here. Even there, you still have pretty high levels of IGM attenuation that you have to account for. And more of an issue is the fact that this IGM attenuation varies along different lines of sight in ways that we don't know. So often studies will have to either stack galaxies at these redshifts in order to average over those variations, or if you do have an individual source, you often have a very high error bar on its derived escape fraction because you don't actually know how much IGM is in the way. So I like to work at low redshifts, less than 1, where we don't have to worry about the IGM really at all. And at low redshift, identifications of Lyman continuum emitters have seen a dramatic rise over the past 15 years or so, starting from just a couple sources known in the early 2010s, and now culminating with the first large statistical sample of Lyman continuum emitters, the low redshift Lyman continuum survey, where we published our first results in 2022. And the Low Redshift Lyman Continuum Survey, or LZLCS, is a cycle 26 HST cost survey that looked at 66 galaxies at redshift 0.3 in the Lyman continuum and deliberately targeted a wider parameter space than previous searches to really try and look at what properties are associated with Lyman continuum photons making it outside of a galaxy. And we have 35 Lyman continuum detections from this sample. And along with past literature samples, that brings us to 50 Lyman continuum emitters known at redshift 0.3, and then stringent upper limits for the remaining non-emitters that in our sample. And thanks to working at low redshift, also we get a variety of information about the properties of these galaxies. So here I'm showing the HST cost spectrum, where we have our Lyman continuum region that we're able to measure, but we also get absorption lines from the redder wavelengths of the ultraviolet and stellar population properties. We have access to rest frame optical data from SDSS, including spectra and photometry, so we can get the nebular properties of these galaxies, their metallicities, et cetera. And the COS NUV acquisition images provide us with estimates of the sizes of these galaxies. So from this survey, we've gained some insights into what properties are associated with Lyman continuum escape. So the first property, one of our strongest correlations, is that these Lyman continuum emitting galaxies tend to be highly ionized. So here, this is the ratio of O3 5007 emission to O2 3727, so how highly ionized is their ISM. And this is the Lyman continuum escape fraction. And our strongest leakers are shown in black points here. And are at the highest levels of Lyman continuum escape, these galaxies seem to have a very highly ionized ISM. Another of our stronger correlations is the compactness of the star forming region. So this is showing the star formation rate surface density. And you can see about above this threshold here, almost all of our Lyman continuum emitters are located in this region where they have very concentrated star formation rate surface densities. And then another property that seems to be closely associated with strong Lyman continuum escape is how blue these galaxies are. This is the UV slope beta, which in our survey is almost perfectly correlated with the UV dust attenuation. So the strongest leakers have very little line of sight dust attenuation, which makes sense as that would also be absorbing Lyman continuum photons. But one thing to notice from all of these plots is there still is high scatter. There's a lot of variation in the Lyman continuum escape fraction for a given galaxy. And there's also diversity too. So even though our strongest leakers tend to be highly ionized, that's not universally true. You can get strong Lyman continuum escape even at much lower ionization ratios. And so this has led us to think about the fact that you might have different populations of Lyman continuum emitters with different properties and perhaps different mechanisms driving the escape in different cases. So here I'm showing the ionization again, O3 to O2 ratio here, and the concentration, star formation rate, surface density here. So combining those two different properties, and this is color-coded by escape fraction. So our strongest Lyman continuum emitters tend to be in this regime here that have very highly ionized galaxies, also compact. These galaxies tend to be the green peas, if you've heard of those. Those are very strong emission line galaxies. They have our highest nebular equivalent widths. They seem to be extremely young starbursts. They tend to be metal poor, low mass. And with their young ages and high ionization in the ISM, we're really probably catching these at their peak ionizing photon production. So they may be objects that are dominated by ionizing radiation and its effects on the ISM. Almost every single one of these galaxies also is detected with strong Lyman continuum escape. So what we're measuring with COST, though, is only the Lyman continuum escape coming in a single direction towards Earth. And the fact that we always detect it from these galaxies must mean that it's coming out in a wide range of angles, assuming these are randomly oriented. So they must have a fairly wide opening angle for their escape for us to always be lucky enough to detect it. A second population of Lyman continuum emitters we have is not quite as highly ionized as the green peas, but it is still quite compact in its star formation. These galaxies tend to have lower equivalent widths, so a little bit of an older starburst, perhaps. They are more metal rich. They tend to be a little more massive. And so this is possibly a candidate for a scenario where supernova-driven feedback might be responsible rather than, say, the ionizing radiation itself. And here, too, we don't always get Lyman continuum escape from this population. So that might be a sign that there are some sightlines that are blocked, and we only detect Lyman continuum escape from particular directions. So in both of these scenarios, I've suggested that feedback in some form might be at work. And we do see evidence that Lyman continuum emitters are associated with feedback. This is work that was recently published by Ricardo Amarin, looking at the emission lines of galaxies in our survey and the kinematics of those emission lines specifically. And he found that the strongest leakers are associated with H-alpha emission lines that have a broader component to them and higher velocity gas. But again, here too, you can see that there's quite a significant amount of scatter here, that the escape fraction can still span an order of magnitude at fixed velocity width. And we really don't know what the physical connection is between the sites of Lyman continuum escape and where these disturbed motions are coming from. We also don't know the cause of these motions either. It could be from supernovae, it could be turbulence, it could be mergers. And the outflows if they are outflows, don't even have to be driven by supernovae. They could be driven by radiation. This is something that has been seen for green pea-like galaxies before. This is, I'm showing here the emission line profile for a very nearby green pea galaxy, Markarian 71. And it has these power law shaped wings to it that are characteristic of outflows being driven by radiation. So we don't know exactly which feedback mechanism is driving the Lyman continuum escape in these objects, just that something associated with high velocities seems to be at work. In order to figure out what type of feedback might be present, one thing we can look at is how old these starbursts are, and so what mechanisms are present in a starburst of that age. So this is work that Sophia Fleury is doing using stacks of various subsets of the LZ-LCS spectra to enhance the signal to noise and get better estimates of the stellar population properties. And so the data points here are the various stacks of various subsets of the sample. And then here I'm showing the fraction of the light contributed by populations less than 3 million years of age, so pre-supernova populations, and the fraction that's contributed by older, more than 8 million year age populations, so post-supernova. And again, color coding by the Lyman Continuum escape fraction. And our strongest leakers populate this corner here, where they both have a significant contribution from older populations and a high contribution from very, very young populations. And so one possible explanation for this is that we're seeing a two-stage starburst, where you have some first population that forms, that then ultimately evolves to produce supernovae that disrupt the ISM. And then you have a second population that comes in and with strong ionizing feedback is able to ionize the remaining channels and produce large amounts of Lyman Continuum photons that we then detect. She's also looked at multivariate correlations with these stacks and among various geometric and age-related parameters, what best correlates with Lyman Continuum escape. And in those multivariate correlations, this young light fraction is the strongest predictor of very high escape fractions. So having some source of very powerful radiation seems quite important. But of course, the caveat here is these are stacks. We don't know what's actually going on in an individual galaxy. And we don't know that these two populations actually have any physical association. This is just a hypothesis at this point. So interestingly, even though we find that there's this association with very young populations, that seems to be different from what's seen in simulations. So this is simulations by Chustikov et al. And this is looking at the ionization of the ISM 03 to 02 ratio versus escape fraction. And they find that the peak escape fractions typically occur at sort of moderate ionization and slightly older starburst ages. Again, once you've had supernova feedback able to kick in and disrupt the ISM. And this is in contrast to where we find our strongest leakers, which tend to be in this very young, very highly ionized regime. And this is not the only simulation that shows this. Many show that supernova feedback is important. These are simulations by Barrow et al. And this is looking at, as a function of time, when the escape of Lyman Continuum peaks in green versus when that 032 nebular ionization ratio peaks. And they're a bit offset because, again, you don't get the peak escape until after your starburst has aged a bit, which is also when it's a little less ionized. So it's not clear what the disconnect is right now between these simulations and observations, whether it's some observational bias, whether there's a resolution factor of the simulations where they're not resolving some key part of the ISM structure that's relevant here. So that remains to be determined and is a bit of a mystery. Regarding the importance of ISM structure, we do see that understandably plays a key role in regulating Lyman Continuum escape. Also, so thanks to the HST COS observations, we're able to get UV absorption lines and measure their strengths. Here I'm showing one of the Lyman series lines showing absorption from neutral hydrogen. And then this is a low ionization metal line from silicon 2. And we're able to measure covering fractions and equivalent widths for these. But as you can see from these spectra, this is a tricky business. These are quite noisy. They're quite low resolution. And unfortunately, we only have G140L low resolution spectra for most of the survey. And even to enhance signals noise, we are often averaging the covering fractions or equivalent widths for multiple lines to get a better signal to noise. We do have higher resolution spectra, but only for a much smaller subset of the survey. And this is too expensive to get for some of the faintest lower metallicity galaxies at these redshifts that just have very weak absorption lines. But given those caveats, we do see that our strongest leakers do seem to have lower covering fractions in this H1 absorbing material. We see signs that the ISM is patchy and that when you have less of this absorbing material in the way, you are able to get more Lyman Continuum photons out along the line of sight. So here I want to just now summarize what we're seeing from the survey so far at redshift 0.3. This is the first large statistical sample of individual Lyman Continuum emitters that we have. And we're seeing signs that this is a diverse population. There's no one unique property that tells you something's a Lyman Continuum emitter. But our strongest Lyman Continuum emitters do seem to be highly ionized, compact, having the presence of some young burst. And their escape does seem to be somewhat line of sight dependent, depending on the covering fraction of neutral gas in the way. What creates that geometry is still to be determined. It seems like it might be associated with feedback, but we don't know what kind. We don't know if there's a two-stage burst or if there's supernova feedback playing a role or if it's just radiation feedback. All of the sort of details as to what mechanism is driving this are still an open question. And our team is doing a number of follow-up studies intending to get both imaging from Hubble for some of these galaxies, deeper optical spectra, infrared spectra for some, higher resolution ultraviolet spectra. So we're really trying to dive into the details of what drives Lyman Continuum escape in these galaxies. But there's still some major open questions that I think HWO is well poised to answer, looking specifically at where Lyman Continuum escapes from galaxies and what feedback mechanism actually drives that. Also thinking about what we've missed in our survey so far, what other Lyman Continuum emitting populations are out there. And then also looking at what sources produce Lyman Continuum emission and what energies escaping Lyman Continuum radiation has. So I want to talk about each of these in turn. First, thinking about where Lyman Continuum escapes, I think it's helpful to show some examples of what these galaxies might look like if we had the resolution to distinguish them in greater detail. So this is the galaxy I alluded to earlier, Markarian 71. It's a green pea galaxy located only 3 megaparsecs away. And it has these two star-forming knots, knot A and knot B. Knot B is about 5 million years old, and it's sort of cleared out this region with a superbubble here. Knot A is only 1 million year old in this location here. And knot A, this little region, is actually producing 90% of the ionizing luminosity of this galaxy. And that little region is less than 2.3 parsecs in diameter. So this is a really, really compact superstar cluster that is the dominant source of ionizing radiation in this galaxy. This galaxy is a relatively low mass galaxy. A slightly higher mass object is this galaxy here, Haro 11, located at a redshift of 0.02 with a stellar mass of 10 to the 10. This is the first Lyman Continuum emitter discovered at low redshift, discovered by FUSE. And it's a fairly low escape fraction, but it does have escaping radiation with escape fraction of only 3%. And because it's so close, we can also look at its structure and see that it too has multiple star-forming regions, knots A, B, and C here. You can see this beautiful, complicated dust lane structure to it. And each of these knots as well has different properties. One is associated with an ultraluminous X-ray source. So there's a lot of stuff going on in this object. And then for comparison, this is one of our galaxies at redshift 0.35, a Lyman Continuum emitter. And this is our COS image of this. And you can see that, whatever beautiful structure is in this galaxy, we cannot distinguish that. We just get one signal and we don't know what is actually going on behind the scenes in this object. So why are we looking at galaxies at redshift 0.3 where we can't see too much detail? We have to, because of the sensitivity of COS. So this is showing the HST COS effective area as a function of wavelength. And then here I've plotted the wavelength that redshift Lyman continuum would show up at. So you can see that at a redshift of 0.1, Lyman continuum shows up around 1,000 angstroms here, where COS is not at all sensitive. Redshift 0.2, it's still not sensitive enough. And really only when we get to redshift 0.3 do we actually get to the part of the wavelength range where COS is sensitive. And so sort of by force, all of our targets have to be at redshift 0.3. But then we lose this utility of having this sort of spatial resolution to be able to disentangle what's going on. So I mentioned this possibility of a two-stage starburst. And we might see something like that happening in a galaxy like Markarian 71, where you have these two knots of different ages close together, where knot B is sort of clearing out this region, and which might make a difference as to whether knot A can have ionizing radiation escape. This is something we can't see for galaxies at redshift 0.3. We can't see whether these different age populations we're picking up on are in any way physically associated, or they could be at completely different ends of the galaxy. We don't know. So I think understanding where Lyman Continuum escapes, it would help to have this sort of spatial resolution. We would also want to isolate both where the Lyman Continuum emitting clusters are and then relate them to the overall structure of the ISM. What is going on with the neutral gas geometry in that region? What is changing the neutral gas geometry in that region? So here I'm showing HARO 11, again, that other Lyman Continuum emitter at much lower redshift. This is a H1 21 centimeter map of HARO 11 that shows that its 21 centimeter emission is tidally offset, perhaps due to a merger. And so this disruption due to a merger might be very relevant for why this galaxy has escaping radiation. It would be wonderful to get 21 centimeter maps for our targets or for other known Lyman Continuum emitters, but that's not really feasible at redshift 0.3. For another local example, this is a Lyman Continuum emitting candidate galaxy that has IFU observations, but it doesn't have confirmed Lyman Continuum emission. It's again at very low redshift. And from this IFU data here, this is a velocity map of the galaxy, and there's this red area shows high velocity gas that's been identified as an outflow coming from the central starburst. That outflow is also associated with this yellow region here that traces high ionization gas. So you're seeing a highly ionized channel coming out from this starburst that could be the outflow, an ionized outflow. That's the region where Lyman Continuum photons are escaping. So this would be a way of connecting that driving mechanism, connecting feedback to the escape of ionizing radiation. But it requires being able to create these sorts of maps, both of nebular data or of neutral gas data, and also figuring out which region the Lyman Continuum is coming from itself. In terms of connecting and relating this to feedback mechanisms, one thing to note is that in these really extreme starbursts that we're talking about that are the galaxies where we have strong Lyman Continuum escape fractions, the way feedback operates in those galaxies could be quite different from higher metallicity galaxies or less extreme ones. So this galaxy, Markarian 71, is a candidate for a process known as catastrophic cooling, where its superbubble formation may be delayed because it's, rather than having a hot bubble around it that expands, basically all its energy is being radiated away. So that changes how this ISM region might evolve. At low metallicities, when supernovae may go off later. So basically, your stars maintain their mass because they have weaker winds, and more of them go into direct collapse black holes. So your supernovae may not kick in until 10 million years down the line. And so that will change how feedback operates in these systems and which processes are dominant in a starburst of a given age. And then, as I mentioned, Markarian 71 also is this candidate for these radiation-driven outflows. So we need to think about those sorts of processes. So being able to have observations of exactly giving us precise ages for the Lyman Continuum emitting regions and then also their ISM properties could be quite useful in figuring out what actually is happening physically in these sorts of objects. So to get that, again, we would need to spatially identify Lyman Continuum regions. We would also want higher resolution ultraviolet spectra to be able to better measure those UV absorption lines, figure out what the geometry of the ISM is along the line of sight, get kinematics for that, and also get better stellar population features to really be able to age date these things precisely. So that's where we're having the spatial picture would be helpful. I think it's also possible that we've not fully explored the parameter space that we need to in searching for Lyman Continuum emitters. So this is work that I've been doing recently, which is taken the results of the low redshift Lyman Continuum survey and used it to generate predictions for escape fractions for galaxies at redshifts greater than 6. And so these are my predicted escape fractions, and this is the magnitude range, UV magnitude range of galaxy samples that JWST is observing at redshifts greater than 6. And this is the actual magnitude range that our survey covers at redshift 0.3. And so all these predictions over on either side here are based on extrapolating our results to a magnitude range we have not actually directly probed. And again, the reason is that our redshift 0.3 samples probe a fairly limited parameter space, at least in magnitude. And we really don't have empirical constraints at low redshift on these fainter galaxies and how much radiation actually escapes them. But these are a key candidate for reionizing the universe, so it's important to explore that regime. And in order to actually be able to detect Lyman Continuum for these really faint galaxies, it would really help to be able to work at lower redshifts where we can get fainter targets, but we would need much better sensitivity at short wavelengths than COSS can provide. There are other candidates as well that we might be missing. I mentioned that our strongest leakers are these green P galaxies that have really strong nebular emission lines. And that's actually a bit odd because theoretically, we would expect that the galaxies with the strongest Lyman continuum escape should have the weakest nebular emission lines. If they don't have much nebular gas to absorb anything, absorb Lyman continuum emission, they should have just weak nebular emission in general. This is showing as you increase the escape fraction of a population, how its emission lines get weaker. And so we may want to explore galaxies with much weaker nebular emission lines and search for that to find the strongest global leakers. There are other proposed ways of finding Lyman continuum emitters, selecting on helium-2 emission, which picks up galaxies with very hard ionizing radiation. This has been proposed as a Lyman continuum emitting population. This is a sample of helium-2 emitters at redshifts less than 0.1. We can't observe the Lyman continuum for galaxies at those redshifts right now. Or another selection has been proposed that we should look at really weak emission from lines that trace the neutral gas of a galaxy, such as O1 or S2. Those are also faint lines that are even tricky to get for our samples at redshift 0.3 and certainly hard to select on at those redshifts. And then if we want to really connect this to populations at very high redshift, we need to think about looking at extremely low metallicities that might be relevant for very high redshifts. And this is showing just some samples of extremely metal poor galaxies in the local universe. And again, getting down to extremely low metallicities, extremely low luminosities is not something we can easily do at redshift 0.3. So to find these sorts of targets, we also need wide area spectroscopic surveys to pick up on these potential emission line selections and find a target list to follow up. Our survey has heavily relied on SDSS to pick candidates. And so any future work would also need to be paired with probably some large area spectroscopic survey. It needs to be spectroscopic rather than photometric because if you'll pick up something like a green P with strong emission lines in a photometric survey. But if you want to select on some of these weaker lines, you only can do that with spectroscopy. And again, we need to be able to go to lower redshifts and to go to fainter galaxies. Some of these candidates, aging starbursts or low metallicity starbursts, may be quite faint. And so being able to actually measure Lyman continuum from those sources would be important. And then a wide area survey would be important also to allow us to find rare objects that might be better analogs or might be of high redshift galaxies or probe parameter spaces that we don't typically get to access. And then just to wrap up, one of the other open questions for all of this is which sources actually produce the Lyman continuum, not just what allows it to escape, but what produces it, and what energies does that Lyman continuum emission have? So I mentioned that the green P galaxies are very young. They have this less than 3 million year old component to them. This is the sunburst arc is a known Lyman continuum emitting galaxy at redshift 2.4 that also has quite a young age, 3 to 4 million years age. And its ultraviolet spectrum shows these features here marked in red that have been proposed to be signatures of very massive stars, so several hundred solar mass stars. This paper just came out yesterday that finds evidence for a Wolf-Rayet population in the sunburst arc, but finds that the models for Wolf-Rayet stars or BPAS models or stellar population models for this galaxy don't produce as many Wolf-Rayet stars as there seem to be. So there seem to be a need for more Wolf-Rayet stars in this galaxy than the models currently contain. And I bring this up just as an example that when we're talking about these Lyman continuum emitters, we really need to worry about what's going on at low metallicities with the most massive stars in these galaxies. We need to worry about how many VMS stars, how many of these 100 solar mass stars a galaxy has, and what their spectrum is, and how they evolve. We need to understand Wolf-Rayet populations. We need to know the IMF at these low metallicities to understand what's producing ionizing radiation. And so to better understand that, we also need deeper ultraviolet spectra to really get stellar features, some of these weak stellar features that can precisely detect some of these populations like VMS stars. We need reference observations of low metallicity clusters to figure out what stars are present and what their features are at these metallicities. And this also needs to be paired with modeling efforts to understand both the IMF and stellar predictions for stellar evolution. And just some evidence that we don't understand this well comes from helium-2 emission. This is showing metallicity and helium-2 4686 over H beta. And there seems to be an uptick where many low metallicity galaxies show this helium-2 emission feature. And that is still an unsolved mystery. We do not know how to get it in these galaxies. It requires 54 electron volts of energy. And it's just a sign that we really don't understand the hard ionizing radiation in low metallicity galaxies. We don't know what sources are producing that. We don't understand their ionizing spectra. And so again, I think getting UV spectra for helium-2 ionizing clusters at low metallicity would be important, looking for stellar population features. And also it'd be interesting to explore the spectral shape of the Lyman continuum itself. At redshift 0.3 right now, we're just getting a data point at about 900 angstroms. Again, with sensitivity to bluer wavelengths, we might be able to start looking into the spectral shape of the Lyman continuum. And if we push to even higher redshift observations, we could get even shorter wavelengths and start trying to see what that looks like actually in observationally. And then stars are not the only thing that can affect the shape of the Lyman continuum. Nebular Lyman continuum emission can also contribute. This comes from recombination to the ground state. This is showing in gray here the escaping stellar spectrum that would be predicted, and in purple the escaping the shape of the spectrum if you include this nebular contribution. This depends, how much this contributes depends on the column densities of H1 that you have. And understanding this shape is quite important for reionization because the cross-section for absorption by hydrogen is wavelength dependent. So your hydrogen gas is going to care as to whether it has a lot of emission coming out at the longer wavelength end of the Lyman continuum versus the shorter wavelength end. And what we are able to probe with our sample right now is just this little window here from sort of 850 to 900 angstroms, which does not give us a good handle on this spectral shape. And this is another area where having high sensitivity to much bluer wavelengths could give us some insights. So just to summarize, I think HWO can add some useful insights into how Lyman continuum is escaped, at what energies, what galaxy populations emit Lyman continuum. And to do that, really having this higher sensitivity in the far ultraviolet would be important to be able to start looking at things at lower redshift, where we can get different candidates, and also where we can follow up those candidates with a variety of other facilities. And not just studying the Lyman continuum, but also getting deeper ultraviolet spectra would be helpful to better understand stellar populations at low metallicities. And I just want to end by showing this is Markarian 71, this H2 region here within this galaxy, NGC 2366, to again emphasize the sort of structure that we might really have here. And this is all the information that we get for a galaxy like this. This is H121 centimeter information. There's molecular gas here and emission line imaging. There's studies of the stellar population of these different knots. And that's helping us understand how these populations are driving feedback in this galaxy. And so this is also, I hope, can emphasize an important question for not just studies of the Lyman continuum, but for galaxy evolution more broadly. All of this is connected to what sources are present in a galaxy, how does their feedback actually reshape the ISM of galaxies? And that's a bigger question than just which galaxies reionize the universe. So I'll stop there and take any questions.
Sorry. I seem to clap faster than I can do the clap emoji. That's fantastic. Sorry, kept going all over the place. So obviously I'll have questions, but I always reserve mine to the very last, just in case I have to jump in or I just dominate the speaker. So who has questions? Either raise your hand or jump in. Let's hear it from the audience. But thank you so much for a wonderful talk. The Zoom call is like I can't stare at people until they give me a question. Yes, there is a question from Yakov. Jump in.
Thanks. Hi, and thank you for a very interesting talk. At the beginning, you mentioned that the number of Lyman Continuum emitters increased significantly. So I was wondering what caused this. Was this an instrument or the survey that you described? Yeah.
Yeah. So most prior studies had not really found many strong Lyman Continuum emitters until 2016. People first looked at Yuri Izotov first looked at the green pea galaxies, and started with a small sample of green peas, and then found that 100% of those seemed to be Lyman Continuum emitters. So that was the first time we actually had any sample, significant sample, and then followed up with more studies of the green peas with more detections. And then that prompted us to start this larger survey where we targeted both green peas, but then specifically looked at other proposed selections for Lyman Continuum emitters on compactness and blue spectral slopes, and compiled a sample of 66 galaxies that had various combinations of these criteria. And yeah, that was really the first large sample that had been investigated in the Lyman Continuum, but building on these first times when we actually had success. Yeah.
Really interesting. Cool. Thanks.
Any other questions? I see a couple of people turning on their videos. I'm hoping that's an indication. No, they're just turning on the video. Oh, yeah, here we go. Stephen, go ahead.
Yeah, and I was very nice. Thank you so much. You always do such a great job with this. I was interested in the comment about the Wolf-Rayet spectra in the green peas, and what do you think is the reason the BPAS models are not producing enough Wolf-Rayet?
So to clarify, this is not the green peas. This is the sunburst arc at redshift 2.84.
I'm sorry. Yeah, the sunburst arc. I'm sorry.
I don't know. I don't know why there aren't enough, other than, it could be the need for a more top-heavy IMF, or not understanding the formation of these stars, whether they're you can get Wolf-Rayet stars also from binary evolution effects. So who knows whether we're correctly modeling that. I was going to say something on, but I don't remember. Yeah. I remember I was going to say. So these Wolf-Rayet stars. So I say these have been proposed to be VMS features, and these Wolf-Rayet features. Rivera Thorson in this paper note that these are closely connected in that VMS stars can evolve into a Wolf-Rayet phase. So these may be sort of the same type of star, but for whatever reason, the models are not producing the strength of this population that's actually the strength of these features that's actually seen in the spectrum.
Right. I note that when we look at the Sloan spectra of our green peas, that I always look for the 4686 line, and it doesn't ever seem to be there. So that really does sort of suggest that different populations are involved with this escape business.
Yes, perhaps.
Thank you.
Okay, any more questions? Any more? Otherwise, I'll start jumping in. But first, let's have some people turn on a camera and ask a question, please. See more. Pop it in. No. I had a question about the sizes. So how did the size get measured? Because you had like a surface density of H beta or surface density of star formation. Are they measured in the actual blue in the star formation tracer, or in the is this the stellar mass tracer?
They're measured in the ultraviolet, the near ultraviolet from the cost acquisition imaging. Yeah. And then the star formation rate there comes from H beta. We also have star formation, we have ultraviolet star formation rate surface densities as well. It just changes which star formation tracer we're using, but the radius comes from the acquisition images.
That was it's like one of those little technical things that sort of like, oh, where did
Yeah.
that come from? Because that's how it gets measured at JWST. So it's nice and compatible. Like the high redshift surface densities are measured in restframe UV. So that's directly matches up. So are you? All right, I'm going to take a break because again, I don't want to dominate the speaker. Does anyone else have a question that isn't, a small technical thing like I just did? All right, second small technical thing, which is about this one, which is so if you have very massive stars, a way I understand it is that if you have them in binaries, they live longer, or they sort of have a different lifespan, and they produce UV for way much longer. So your star formation rates suddenly drop because actually, you're still seeing the UV from an older generation, or at least that generation lives a little longer. So could that be an effect? Because that's something that was being incorporated into BPAS.
It's something that's incorporated into BPAS, which is what the these models that I'm showing on this page are using BPAS. But yes, you can have the binary models in general extend the production of ionizing photons over a longer time period, because you can get lower mass stars can merge into and create a new high mass star at later times, or you can have accretion from one star onto another that again can produce a more massive star at later times. So that is something that can potentially help in terms of getting ionizing photons out at later times. And yeah, I would say we really don't understand yet what the ages, the role of age in all of this. I think it's quite important. And in terms of understanding which populations actually dominate Lyman continuum emission, what ages they have, and then what their populations of stars are. Do they fit these binary models? Have they had supernovae? Is that what is supernovae plus the binary stars the key, or is it something different? I don't think we know yet.
So this was sort of linked to the age ladder that we're talking about in various groups. So that would be good. I came across this because we're using UV or restframe UV for star formation estimates, and even at low redshift, you're getting that issue. It's like, am I looking at binaries or not? Oh yes, and the last question was, so we're getting deep H1 observations soon. So redshift 0.3 is no longer extreme high redshift for radio observations. So this would be a thing where you could get a direct H1 map of such green peas, right? So this is a potential very soon to happen kind of observation. What would that tell you in addition to the Lyman continuum, right? So now you have an idea of how you might have an idea of how compact the ISM actually is, where the H1 sitting around. Would that help?
Yeah, I mean, I think I would love to get H1 information for any of these galaxies. I think it'd be useful to know whether they are deficient in H1 gas and in some way, in some global way. If you can see any sort of disturbed kinematics in the H1, suggestive of mergers, that would be interesting. I guess it depends on what the H1 resolution is, whether you're getting a total mass or whether you're actually able to get any structure. But any H1 information would be useful, since that's what's absorbing the Lyman continuum. From lower redshift observations of green peas, there is some evidence that some of those may be deficient in H1 globally. But we are in this sort of annoying regime where the things where we can study in great detail are the things that we don't have Lyman continuum for, and vice versa. So we just have to sort of assume that, well, if we assume that these Lyman continuum emitting green peas are the same as some slightly different lower redshift green peas, then maybe they are also H1 deficient. But it would be great to actually test that on the same objects that we have the Lyman continuum sections for.
That's okay.
Steve has his
again,
hand
I'm
up
doing-
first,
Yeah,
and then Alessandra can go next.
I would defer to Alexandra since I've already asked a question, but I would like to comment with an idea afterwards. Go ahead, Alexandra.
Yeah, sorry, I actually had a comment about the deep H1 maps that are coming. So when you refer to this, do you refer to LaDuma and such surveys or something else?
I would be, but because I'm the PI of LaDuma, but there are other well, one of the three, but there are others coming as well, and there are options to do, for example, H1 absorption within in radio continuum as well. So that would give you a column density. Just starting we can start thinking about where these things overlap, where the sample is high redshift enough that we can see the Lyman continuum and low redshift enough that we can actually see the direct emission or absorption. Just curious if that would actually add to the whole picture. It sounded like it, but
Oh, absolutely, absolutely. I think if I had a priority of sort of multi-wavelength data, I would like H1 would probably be my personal priority, since that is the relevant quantity for Lyman continuum escape. But yeah,
it's coming.
good.
All right. Steve had something and then he ran away, I think. Yes, see his bookcase. So, okay. Was that a comment? Your hand is still up.
He's back. He's back.
He's back. Okay, Stephen, you can give your comment.
Yes, sorry. My wife just had hip surgery, so I had to attend. There was something that came up in at the STARS conference meeting yesterday, where Danielle Calzetti showed that clusters that were young tend to have a lot of dust attenuation, but it also showed that young clusters could also have a lot of UV as well. There was a very broad range, and I was talking with Cody Carr about this, and I came up with a thought that maybe there's a sweet spot in age for Lyman continuum leakage, in that, when you have lots of young stellar objects, you're forming out of a very cloudy environment, and that as you get to sort of some energetic age where winds are starting to clear the natal cocoon, that you break through and you start to produce a lot of escaping radiation. But then as the cluster then ages a little bit more, and you lose that compactness, that you start to get into late O and early B stage, that you're starting to produce more dust again, and that the dust then sort of recoalesces and enshrouds, and makes it more difficult for Lyman continuum to escape. So there was sort of suggest that there may be a sweet spot in age over which things really start to kick up in terms of Lyman continuum. But then once you get to a certain point where you start to form a lot of dust, either due to supernova or just interacting binary winds that can produce an awful lot of dust, that then that Lyman continuum leakage from a cluster would go down. This would be very interesting to study. There were other people that were showing cluster data from JWST, where you had a very compact cluster, and it had not much dispersion with the PA emission, and then there were instances where there were complex clusters that showed a broadening in the PA emission, and then another set of compact clusters which showed a hole in the PA emission. So there might be some connection between in JWST. We're looking for holes in the PA emission might show where clusters are starting to burn through and escape Lyman continuum. That's just my comments. This is we thought this was a good idea yesterday.
Yeah.
We talked about it.
Well, we will have JWST observations for some of these to be able to look at their PA emission to test that. But I think it would be really great also to get simulations, high resolution simulations of this sort of the formation of these sorts of really extreme compact clusters. Because I don't know if I mean, some of these things are just so extreme, like I'm thinking about Markarian 71, that I don't know if our sort of normal observations of clusters or of cluster formation apply in that sort of extreme regime. Something that I've wondered about is even the star formation efficiency. You know, do those clusters consume a lot of their surrounding material in the formation process, even before feedback kicks in, or what's the structure of of that birth region? How clumpy is the dust distribution and the molecular gas distribution? If it's born sufficiently clumpy, then maybe you don't even need much feedback at all to be able to sort of instantaneously have Lyman continuum escape. But that depends on the birth conditions in that region, and I don't know what those are in this sort of extreme compact cluster regime.
Looking forward to an instrument we can finally make these observations.
We're coming up on the hour, and yet I still have another question. So I will probably sneak that in later, or in the nowish. But anybody else who has a question, let's go with the audience first. Or is it everybody else has switched off their screens? Okay, I'm going to do it.
I didn't mean to put Steve or Alison on the spot, but if you want to give a quick plug for the iPhoton working group for HWO, feel free to do that. You don't have to, but if you want to.
Yes, no. So there is an Ionizing Photons and Their History science case working group as part of beginning to develop science cases for HWO. Stephen and I are co-chairing that, and I know I see a lot of familiar names. We're having our kickoff meeting on Tuesday morning next week. So we can, I think it was sent to various lists. If you haven't heard it, shoot me or Stephen an email or ask Aaron. I think Aaron knows. We would love to see all of you interested folks there next week as we begin the process of thinking about these kinds of related questions for the next Great Observatory.
Thank you, Alison. Okay, I think we come to the top of the hour. Thank you all for joining us. Our next seminar will be in 2 weeks, and see you all there. Thank you, Anne. Thank you, everyone. Bye-bye.
Thanks much for a great talk.